Hello. Sorry for the somewhat scuffed, messy room setup, but I do have another FPGA project that I've mostly finished. It's not completely finished. Um, and I've turned my webcam on because I wanted to show you guys how it actually works on the FPGA side of things, although a lot of it is going to be from the screen, specifically Terraterm. So I've done an FPGA implementation of AES-128 encryption. If you don't know, my documentation, GitHub is in the description, and also if you're watching through my website, the GitHub should be in the website. But AES-128, very reliable way to encrypt data, approved by the NSA. And the most surprising part about it, the one that surprised me the most, is that it's actually not that hard to implement, especially in software, and in this case, hardware. All you need is binary arithmetic, and by binary arithmetic, I mean you just need to know how to do an XOR gate. Like addition isn't really a thing because when you're adding in Galois fields, which I'll be talking about later, you're basically doing an XOR, right? You also need linear algebra, and by linear algebra, just matrix multiplication. Just need to know how that works. And basic Galois theory. And this sounds scary at first, but this makes everything easier, especially in the field of like encryption and cryptography and stuff like that. Um, so AES, and before I explain anything, let me just actually showcase you what's going on here. So I already have a little bit here. So this switch resets everything. The LED here means that the clocks are locked, meaning that they're stable. Because I have two different clocks working in the design, and I'll show you later why. And now I can just put whatever here. I can just type whatever, and when I can type forever, and this mechanism will be explained later. Like you can hear me clacking right now. And if I press enter, it's gonna output some keys here. And spoiler, this is an obvious limitation of the design. There are blank ASCII characters here, and that's because not all hex characters have a visible ASCII representation, especially in Terraterm. Um, but yeah, that's one of the things that I have to work on. We'll talk about that later. Okay, so AES works with 128-bit inputs, two of them. One of them will be the plain text, the message to be encrypted, and the key. So AES-128 has 10 rounds of this image right here. But first, before you do anything, and this is something that a lot of people miss, is that you have to do a bitwise XOR between the cipher and the plain text first. And then you do start the 10 rounds. So you can see here my poorly drawn diagram. Substitution box goes first, shift rows, mix columns, generate new key, and then XOR. I will explain all of these later, but basically there will be 10 rounds for this. I believe for AES 256 it's 14 rounds, 128 is just 10 rounds. And after you generate new key, you go back to substitution box over and over. A few things to note here is that the last round, the 10th round, will not include the mixed columns because it does not add any form of security at all. Another thing to note is that generating the new key does not need mixed columns as a prerequisite at all. In fact, you can do them parallel. It's just that in the design later for the FPGA, each consecutive part will handshake with one another, saying, "Hey, I'm done. Can you do this?" And then blah blah blah. That's why generate new key is part of this sequence and not necessarily parallel. I tried that; it was a little complicated. I'll talk about that later. So before I explain these, and by the way, if you already know how AES works, you can just skip. I'll probably timestamp it. Um, Before we do anything, it makes it easier to split the 256-bit, 128-bit message into a 4x4 byte array. So B naught here is the most significant byte, and the least significant byte is B15, and you guys know how that works. It's yeah, yeah, very useful. So substitution box. Basically, it's just a lookup table, right? Like you have a huge lookup table. Um, but if you want to derive it on your own, which I didn't do in my hardware, I tried. then it was too complicated. I mean, it's not that complicated, but I was just a little lazy. You just use a lookup table. Um, and again, if you want to derive it on your own, you can use basic Galois theory. And if you don't know how Galois theory works, you can just search up Galois fields with 2 to the power of 8 elements. And how that works is very similar to like binary logic. So first, if you want to do that, if you want to use a substitution box, you take an input x, and then you do the multiplicative inverse in the Galois field with 2 to the power of 8 elements. And this is the expression, so it's the Galois field with 2 elements. And this right here is the irreducible polynomial here in the denominator. That's the irreducible polynomial that we're going to be using in round key generation as well. After you get the multiplicative inverse, you can apply this transformation. These are ones or zeros, so you take a byte. The x here is a byte, and then yeah, you do the affine transformation. You can see a pattern here. It's pretty simple. Next is shift rows. This is really easy. You just don't shift the first row, shift left the second row, shift left twice the second row, shift right the third. I meant first, second, third, and then shift right the fourth row. Mixed columns, I had a typo here, but basically this S is the result. Ignore the equals here. I don't know why I did that. LaTeX things. So you have this constant, and then you multiply it to this, to your byte array. And again, as I mentioned earlier, if you're multiplying something by 3, what you're actually doing is you're not, usually in binary, if you're multiplying by 3, you shift left and then you add. Here you shift left and then you XOR. This is because, again, we're working with Galois fields, and not necessarily like pure binary, like binary representations of integers, right? Yeah, I already suggested watching a quick YouTube video. A lot of good videos on YouTube explain Galois theory pretty well. Or if you're interested in this type of stuff, you might have known it already, or you might have skipped this part. Round key generation is a pretty long part. I'll try to explain it as best as I could. But so we start from the very first key, the key that you input, right? And when you lay it out on the byte array, you take the columns, and those are the words. Again, correct me if I'm wrong, but yeah, you take the 4 columns, and they're called the 4-byte words. Now the goal is to generate the other 40 words, because you need 40 more words. 10 times 4, 10 by 10, I mean 10 rounds. So for an arbitrary group of words, and this has to be W0, or a multiple of 4, has to start with a multiple of 4. We generate the next 4 words by taking the last word, W sub I plus 3, and do the following. So we rotate the word by 1 byte, left shift, and then you perform a substitution box, like the same substitution box here, use a lookup table, and XOR the resulting byte with a round constant, which is different for every round. So this round constant, I didn't lay it out here, but yeah, there is a round constant, and it's slightly different for every round, which is why you get the different results when you XOR it. And once you derive W sub I plus 4, you can get W sub I plus 5, W sub I plus 6, and W sub I plus 7. You just XOR a lot of this, right? So that's all. That's literally it. Again, round 10, remove mixed columns. Copy and paste this link if you want an in-depth explanation. This is where I learned a lot of it from. Purdue engineering course, really good course, really good lesson. Self-studied all of this, mostly from Purdue. Now let's move on to FPGA implementation. This was interesting because, as you can see here, data transmission will be done through UART. I didn't know what the heck UART was, right? So, yeah, I didn't know what UART was. And the encryption part of this is actually really easy. you, as long as you know how to do this stuff, it doesn't take more than like 20 hours to implement it. You just have to, just focus for a long time and to do the code. The hard part was learning UART from scratch, like all of the buffers and stuff, like the clocks, baud rate, stuff like that. It was pretty difficult, but we'll start with the easy part. We'll start with encryption. So every part of a round, S box, shift rows, mixed columns, round key. S box, I use a lookup table. Just didn't bother with Galois theory. Um, there's supposed to be a hyperlink here, but I can't really click on it. But I just copied the lookup table because I didn't want to type everything out. Um, there was already someone who did like AES. I didn't copy everything. I just copied the lookup table. And shift rows is just you. It's just zero logic levels in between, right? Like you just transfer a byte into another byte. You have a new 128-bit output. Mixed columns, I made the input 4 bytes, so 1 word for one component of mixed columns. So in the final design, each round will have 4 of these components. Okay, round key is is a really long finite state machine because you have to do all of this stuff, right? And I made sure to pipeline it correctly. I don't know how correct it is, I'm gonna be honest. But yeah, Galois theory. And what I mean here by Galois theory is just whenever the whenever it's more than 8 bits, I just XOR it with an irreducible polynomial. It's not really complex Galois theory, like you just XOR, right? And so each round module will have I will have 9 round modules. I think I call them prelims, preliminary rounds, whatever. Each round will have all of these parts, and the round final will have everything but mixed columns. And I want to make round final separate not only because of mixed columns, but I wanted to transfer it to the TX using different signals. Yeah. So in the latter half, you guys don't get to see the difficulties that I have to deal with. Stuff was being transferred more than once. So if I just put one input in, it does encrypt it properly. Like I test benched everything, every part, right? I test benched it properly. It does output the correct thing in tera term, but it outputs continuously. So the TX module, the one I will talk about later, needed to find a way to say, hey, I've already received it, stop sending me stuff. And so what I did was that each and every round here, like substitution box for example, if the substitution box is done, it tells shift rows, hey, I'm done, here's the data, do it. Shift rows does the same thing, hey, do this, mixed columns does the same thing, over and over until the final one, generate key, and then you XOR, tells the TX module, hey, I'm done. You don't have to, you can do your thing. And the TX module will say, hey, I've received it, stop sending me stuff. So that's basically what I tried. It's like a handshake mechanism. I don't know if the wording is precise here. Yeah, so when the user presses the enter key, so as you saw earlier, if I press the enter key, it will send a signal to the first substitution box saying, hey, here's the data, I'm not going to send anything again. And I used 5 test vectors. It was fine. Nothing too special. I expected it to work because I test bench every single part before testing the encryption module. Okay, so the TX module, this was a little difficult because obviously the encryption module and the TX module are working with different clock rates, right? Basis 3 has a baud rate of 9,000. So it was hard transferring data and making sure that data is being sent, handshake mechanisms are working properly, and stuff is only being sent once. I already mentioned, had to learn a lot of it from scratch. And there will be 3 parts. First, an intermediate, a buffer, and then the transmitter. I'm going to be honest, I don't know if this intermediate is necessary. It just solved all of my problems, right? So transmitter, the last part of this is just your usual UART transmitter. You can just get it from some GitHub guy, but I made it from scratch for the fun of it and for learning. Now the intermediate serves as a medium between the encryption module and the buffer, the buffer I will explain it later. So whenever the encryption module is done, it will send the ciphered text to the buffer and saying, "Hey, here's the text." Um, and yeah, it is notified when the encryption module is done. And when the buffer is ready, it receives a signal from the buffer saying, "Hey, I'm ready. So pass me the message." And so um, this works because the buffer works at a slower clock rate. So whenever it sends the signal that it's ready, it's going to pick it up immediately by the intermediate, right? Because it's working at system clock, which is like 100 megahertz. Yeah, and so this solved like basically half of my problems, right? Because it was difficult trying to do this with different clock rates. Like technically, I can have the intermediate inside of the buffer, like the functionality of the intermediate inside the buffer, but it was difficult for me, and I didn't want to handle two of those things in one component, so I just did them separately. So the buffer takes that 128 bits, right, and sends it byte by byte to the transmitter. See, the usual transmitter that we work with, right, is only handles 1 byte and then does it bit by bit, does it serially to parallel, and then transfers it to teraterm here. And this is necessary because you're sending byte by byte, right? And so I had this transition state diagram that I drew in Excalidraw, like, but yeah, so it's here. Um, I think yeah, I'll explain it. Um, so message ready means that like the entire message is ready. Um, like the 128-bit signal has been received, and if it's ready, um, byte counter is 16 because we're sending 16 bytes. Um, and it just sends the byte one by one. Here, this is a wait state, nothing happens here. Wait state, nothing happens here. It just sends the byte one by one until the byte counter goes to 0. In that case, everything has been sent, and it goes back. Literally just that, right? You take the whole message, do send byte by byte, and the message ready here is actually from the. This might not be right. This is not message ready. This is byte ready. I will fix the GitHub. I'm sorry. Um, yeah. So this is byte ready, and that means that the transmitter module, is done with sending that 1 byte and is ready for the next byte. Right. So they're just shaking hands with one another, right? Yeah. And I also have an RX buffer. Works almost the same way. The same thing. Um, Here, the RX side does not have an intermediate supply. Um, the UART clock is slower than the system clock. So like you really don't need an intermediate. Like the system clock is going to pick it up pretty fast. So there will only be two parts, receiver module and the RX buffer. Code and details about UART reception. It's online. I made it. Um, I made my own. And I'd also like to explain the RX buffer. I wasn't sure on how to do this, right? I just needed, I only had teraterm to receive the user input. And so I was wondering, how do you do this? So I made the user have to input um, 256 bits, and if and the user can type whatever they want. Obviously, one key is 8 bits; it's a byte. So if they put nothing and they just straight up say, "Okay, I'm gonna enter," the code is gonna be all zeros, like all bits are zeros, right? Just a whole 256 bits of zeros. Now, if they fill everything up, that's good, fine. If they fill half of it, then the second half will be just zeros. But if they fill the entire thing, and they still haven't pressed enter. They entered another key. What I wanted was that it wraps around. So for example, if I have all A's, right, in the two in that plain text, and then I write a B after I did 16, is that right? Yeah, whatever. 16, no, it's not 16, 32 A's. I press A 32 times, and then I press B. It's going to be B and then 31 A's. And why 256? Well, the first 128 is going to be the plain text. Next 128 is going to be the bit, the key. And I had an example here. I should have just read that. But here's transition state diagram. 3 of the states are wait states. They're my favorite. You know, you can just sacrifice some resources if you have a small project in order for function to work. Yeah. So I mean, it's like the inverse of what happened earlier. Um, yeah, it's just data enter, and then it fills up. And the difference here is that the count is being filled up. It has mod 32 because you want it to wrap around, right? Like you don't want it to go from 32 to 0 and then -1. That's not how it works. Yeah, basically the same thing. And that's basically the entire project, right? Obviously, there's a lot of there's a lot of limitations. Being obvious one being not all of them are gonna be visible. Like there's some weird ones like the triangle one, right? And I think there's a lot of other stuff, but obviously there's like some there's like a delete, you know, like something that cannot be like enter key, or like some of them becomes like an exponent, a fractional exponent, right? Just how ASCII works. Um, yeah, and that's the first one. And the second one, yeah, the receiving side of things is also weird, right? Because you can only enter stuff from the keyboard, right? And you cannot do the enter key, right? Because the enter key sends it. But yeah, and you can't do zeros. You can't do 0 1, I think. Yeah, the hex 0 1. You can't send that byte at all because they're not in your keyboard, right? Um, I can study up on ILAs to just confirm that everything's happening correctly. Right now, I'm just matching um, whatever the visible letters are to the actual like ciphertext, and I'm just doing like a converter online. It's pretty cursed. And another cursed idea that I have was to just whenever the encryption module is finished, I have a lookup table, and then that will transform it to their hex values. But then I would have to transmit their bit representation to the transmitter module. That's, I mean, it can work and it's not that hard, but it's somewhat cursed. Like a, an intelligent person would just like have a separate software to just like, hey, input your hex values here, or figure out a way so that the tera term will receive hex values, right? Yeah. Some of the weird glitches that I've had. Um, Most visible keys are correct for some of them. Okay, all of them. 99.99% of them. It's correct, right? I've tried everything. But there's some weird stuff that even though they're mostly correct, they just like do line skip, right? So we can actually test this out. I'm gonna do a reset, and I'm just gonna press A, and I'm gonna enter. See, there's a line skip here. So that's weird, right? So it's gonna be one of my priorities. Probably need an ILA. I need to study up on that, right? And I already mentioned external software probably to be able to send and receive bytes. Yeah, I mean, that's everything basically. Like, this was it's pretty basic. You have UART clock, TX clock, and UART and TX UART is basically RX clock, and I needed that to be 8 times faster because of oversampling. Um, but yeah, it's very basic. It's just really fun project, right? Because I'm new to cryptography and stuff like that. Yeah, and this is basically one of my first ever projects, like personal projects that's of respectable size, and I've worked on this for like 5 to 6 weeks. Um, yeah, and I haven't looked at other implementations yet, so what I'm doing might be unconventional. I did just create a virtual clock, 100 megahertz clock. It passed timing requirements. Um, but yeah, I mean, that's all. And if you have any questions, suggestions, or comments, just email me. Here's my email. And I will be working on another project related to my student group that's working for NASA in U Chicago. And my next project will be doing what they want me to do, which is, as of now, is forward error correction, some borderline digital signal processing stuff. So yeah, I'm looking forward to that. Yeah, that's all.